Chemical reaction and equilibrium conditions become important in many industrial processes that occur during energy conversion, like combustion. As the temperatures in the combustion product are high, one application is the industrial process. That occurs during energy conversion. Combustion, energy conversion. Like combustion. As the temperature in the combustion product are high, a number of chemical reactions may take place that would not occur at low temperature. Typical examples of these are dissociators that require substantial energy to proceed and thus have a profound effect on the resulting mixture temperature. To promote chemical reaction in general, catalytic surfaces are used in many reactors, which could be platinum plates, for example, as in a three-way catalyst converter on a car exhaust system. We have previously shown some of the reactions that are important in coal gasification, and some of the home works have a few reactions used in the production of synthetic fuels from biomasses or coal. Production of hydrogen for fuel cell application is part of the class of process. Production of hydrogen. Production of hydrogen for fuel cells. Is a part of this class of process, and for this is important to examine the effect of both the temperature and pressure on the final equilibrium mixture. Pressure and temperature are important. One of the chemical reactions that is important in the formation of atmospheric pollutants is the formation of NOx, which takes place in all combustion processes that utilize fuel and air. And another application is one of the important reaction is formation NOx from combustion processes that utilize fuel and air. Formation of NOx happens at higher temperature and consists of nitric oxide and nitrogen dioxide. Usually NO is NOx at high temperature and mainly use NO and NO2. This form of the nitrogen in the H through the following reaction called the extended Zeldovich mechanism. Extended Zeldovich mechanism. You have three reaction O plus N2 NO N plus O2 NO plus O and N plus OH OH N plus H. Adding the first two reactions equals to elementary reaction in the table. The four O2 plus N2 2NO. In equilibrium, the rate of forwarding reaction equals to the rate of the reverse reaction. The rate of forward reaction equals the rate of the reverse reaction. However, in non-equilibrium, that is not the case, which is what happens when NO is being formed. For smaller concentration of NO, the forward reaction rates are much larger than the reverse rate, and they are all sensitive to temperature and pressure. With a model for the reactions rate and the concentrations, the rate of formation of NO can be described as this relation, the rate of formation of NO where P on P exponential of the rate of formation of the NO in the Zeldovich mechanism. Where let me write the relation again. The YNO on D G YNO on TNO TNO CT is the equilibrium NO concentration, and TNO is the time constant in seconds. For peak temperature and pressure, as is the typical in the engine, the time scale becomes short, so the equilibrium concentration is reached very quickly. As the gases expand and temperature and pressure decrease, the time scale becomes large, typically for reverse reaction that removes NO, and the concentration is frozen at the high level. The equilibrium concentration for NO is found from reaction for equilibrium constant K. According to this relation, the expression, we can express that the molar NO at equilibrium O2E to model the total process, including the reverse reaction rate. A more detailed model of the combustion product mixture, including the bottled gas reaction, is required. The simple model does illustrate the importance of the chemical reaction and the high sensitivity of NO formation to peak temperature and pressure, which are the primary focus in any attempt to design low-emission combustion process. One way of doing this is by steam injection, shown in the picture before. Another way is a significant bypass flow. In both cases, the product temperature is reduced as much as possible without making the combustion unstable. A final example of an application is simultaneous reaction, including dissociations and ionization in several steps. When ionization of the gas occurs, it becomes a plasma, and to a first approximation, we again make the assumption of thermal equilibrium and treat it as an ideal gas. The many simultaneous reactions are solved by minimizing the Gibbs function and explained in the end of section. Figure provided here shows the equilibrium combustion of air at high temperature and very low density. Show the equilibrium composition of air at high temperature and very low density, and indicates the overlapping region of the various dissociation and ionization process. Notice, for instance, that beyond 300 Kelvin, 3000 Kelvin, there is virtually no diatomic of oxygen left, and below that temperature only O and L are formed. This area. Anyway, this is the end of this chapter. Summary of the chapter and key concepts are the next.